Hi everybody, this is Tor Storley and I am back with another video. In this video, we are going to take a look at how you can create a basic time value of money financial library inside a DuckDB macro setting. So in other words, we are going to create it using SQL syntax, using DuckDB's built-in table functions and scalar functions. Now, let me just take one step back and explain why I'm doing this. I have been trying for a while now to create the community extension using financial functions, the basics, like present value, future value, internal rate of return, net present value, those type of things. And I tried to create in a few different languages, but I'm on a Windows 11 machine, and so far I only had problems. And I've been using Claude as a source and Gemini to try to sort my problems of getting this to compile. However, I've been unable. I created a financial library in C++, I created one in Rust, and I also created in Go. But I cannot get it to work on my machine. It's just one thing after another. And I wasted too much time on this. So bottom line is, if you're going to try to create a community extension, you probably should use Linux and Ubuntu, because I have no way of doing this in Windows. And believe me, I tried to download compilers for C++. I tried the Go libraries. I tried the Go templates and all that stuff. But I just had a lot of problems. So, in the end, I just say, hey, if I'm going to create some financial functions, let me just use good old SQL. So I went back and forth and I talked with Claude, and now there's a new model called Claude Sonnet. I think it's 3.6 or 7, I think. I can't remember. But anyways, a lot of iterations and corrections and asking more questions. I came up with 3 files that I've been loading into a DuckDB database so I can actually run some financial functions. Also, comparing it to the results in Excel, making sure that it makes sense, and also another library called numpy-financial, which is a Python library for doing the same thing. So after going back and forth and trying some of these functions, this is what I came up with. So in this video, I will show you what I ended up with, and we'll look at a few of these functions and see what they can do. Okay, so here I'm in Notepad++, and this is the output of some of these functions. So there's like 3 types of function, if you will. There's these basic time value of money functions, and you can see these are the regular future value, present value. There's the payment function. There is the number of periods function. And these are functions you should be familiar with if you know financial functions in Excel. You also have the interest portion of a payment. You have the principal portion of a payment. That is when you're creating amortization schedules for mortgages, etc. You have net present value when you have cash flows, when you have an initial cash outflow and you have expected cash inflows from a project. You have modified internal rate of return, and you have an amortization schedule. So you can see these are different types of macros. Some of them are scalar, some of them are table. Like this amortization schedule is a table macro. And also there's a lot of descriptors here, so you can see what the formulas contains. And you can see this is the code and the inputs, the parameters, in other words. And there's also, if you have defaults like future value is 0. Again, there was a lot of issues here because DuckDB is not a programming language. It's database, and it uses CTEs if it wants to do recursive stuff. So you can't really write a for loop or loop through stuff. You have to basically use these recursive CTEs, so common table expressions. So it becomes more clunky and is not as efficient. And in some cases, when you're trying to do like an internal rate of return, where you have to use iterations, when you use something like this Newton-Raphson conversion formulas or functions, I should say, it becomes a lot of looping, but you have to run SQL queries in order to make it work. So it becomes a lot more complex. So as you can see here, I got this file that contains the internal rate of return code. And it's not pretty, but it's using CTEs, and it creates these holding names, if you will, that will be iterated over and then refer back to the previous one. So S01, S02, etc. And then the formulas are inside these select statements here. So it becomes very cumbersome. And unfortunately, I would love if I could write this in C++ or Rust or something that is super efficient, because it will go in a split second time to do this. However, I ended up with this, and it's not super slow, but it's not super fast either. But anyways, this is the code, and there's also some usage examples here, as you can see. So you can try this yourself. And I'll make this code available out there on my GitHub repository. But I'm not going to step through all this code, because you can spend a lot of time in here to try to explain everything that is going on. There is this time value of money macros. Okay, and there's also some quick queries you can run down at the bottom here. And some of them are based on my amortization schedules that I did in Excel. Some of these are based on what you can find out on this numpy-financial library, particularly for the internal rate of return calculations. And there's also this XNPV and this XIRR. And what those things are doing is, in addition to doing a regular NPV or regular IRR, these factors in unequal time intervals. So when you're passing in parameters, you have to pass a discount rate in, but you have to pass in the cash flows. But in normal calculations for internal rate of return and net present values, you assume equal time spans. Here, however, you can put in unequal dates, meaning it could be January 1st, it could be March 3rd, it could be, so they break it, it's not evenly distributed. And for example, you can see it right here as a calculation where you have a guess rate or discount rate. In this case, you have the cash outflows and inflows here, and then you add the dates that corresponds to these cash flows. So it becomes more date-based in this case. So that's when you have these X in front of NPV and IRR. Okay, just to point that out. So again, it's a lot of code here, and you can look at this yourself, and you can, copy paste whatever you need to get out of this and try it for yourself. But it's getting ugly, as you can see, when you're dealing with this, because you have to do all this recursive stuff, and you have to refer back to it, as you can see down here. So what I have done is, I take those 3 files and I copy it into a folder. So I named this DuckDB underscore TVM, which stands for time value of money underscore macros. So here are these 3 files. And then I have this script here that I'm going to use to load this stuff. So the first thing you need to do is go and open up your CLI. So I have one here, and we're going to run this against the memory database, because I'm not going to create a new one. Normally, you would probably create a database in this case, and you would say open, and then your path and the file of the name of the database you want to actually put this stuff into. But I'm just going to leave it like this inside this memory database. So the first thing we need to do is load those macros into DuckDB. So how do you do that quickly? Well, one thing you can do, you can actually say something like this. So let me paste that in. So notice I'm loading these macros by saying .read and then the file path. And this is how you have to do it in Windows. I don't know how you do it in other environments, but this is how you do it in Windows. Okay, so now it's there. And then what I want to do is, I don't want to run it in this CLI. I want to make it a little more easy to read. So I'm going to open up the DuckDB UI by call start UI like this. All right, so let's run that. And what I did was I created a notebook, and I called it time value of money financial macros, as you can see up here. By clicking this and say, start adding some stuff in, give it a name, and then start adding a bunch of cells. What I'm telling you here is that the functions that I'm using are based on Excel and numpy numpy-financial functions. So they match that kind of construct, and that's what those macros are doing. And if you are interested, you can go here to find out about DuckDB formatters. And the reason I'm referring to that is because most of my functions below use formatting for the output, so it looks cleaner and nicer. And if you want the formatting syntax, you can go here, okay? So that's for DuckDB formatting. So just so you can see it for yourself, let's just open this and paste that in. And when you go here, you can see these are the formatters in DuckDB. And what you do is you can use this format function, and you can use this kind of syntax if you want to. And again, you're going to see this in my queries. The other part I want to point out is that this numpy-financial will give you these input values, and it will give you the result. This is based on this link here that I posted. And also, you can see this is the output you expect. Okay, so the first thing we want to do is verify that because we opened this notebook, but we loaded the macros into that memory, we got to make sure we're pointing to memory here because we haven't attached any database yet. So what I want to do is I just want to see if those macros are actually in there. And you can use this DuckDB functions query here, meaning the function, and select from it to find out whether they exist. And again, we created table macros and we created scalar macros. So you have to specify what you're looking for. And it's probably a good idea to search under main because that's where most likely it will be put. And then we do a sort on the bottom here. So here you can see, let me minimize and get rid of these. So here you can see these are the output that we're getting back from that running that query. And there's quite a bit of functions listed here. So we can also hone in a little more. These are the functions, or the macros, I should say, that I created. So let's see if all those are represented by doing a count. And there should be 12 of them if we are good. And it looks like the 12 of them are there. The next thing we can also do is look for the name and make sure that they are there. So here you can see the amortization schedule is a table macro. So is the internal rate of return and the modified internal rate of return, as well as the XIRR, meaning the time gapped type of internal rate of return, the one that takes into account different time spans. Okay, so you can also, if you just want to look for a portion of a name, like you want to find all the functions that has IRR in them, you can run a query like this, and here you can see MIRR, XIRR. All right. And so now we can start testing some of these time value of money queries. So first thing we can do is test this future value. Okay. So I'm having some inputs and I'm taking the rate divided on 12 because I want a monthly rate. But when you do that, the number of periods has to also be calculated as multiplied by the number. So if you divide the rate by 12, you have to multiply the number of periods by 12 to make sure you're in the right time frame. And you have some additional values here you can see for future value. And again, go back to the text of the functions, go back into Excel and look for the future value formula in case you want some more description of what's in this one. So let's run that. And as you can see, I'm getting nicely formatted output because I used the format function. And I'm doing 2 decimals, and it's a floating number, as you can see here. And I put a $sign in front of it. So it's formatted as text here. So as you can see, that's the result of putting in these payments, and the future value, the present value is -100, etc. All right, so let's run another one. And again, you can verify this in Excel. Just put in the same stuff into the functions in Excel and see what you're getting. All right, we're going to go fairly quick through this because, you always have to go back and check that in Excel if you want to match it with something. So this one is the present value is -100 when you run it. Here we're calculating the payment function. So again, if you take this rate, annual rate is 7.5% divided on 12 months. And therefore the number of periods becomes 12 months times 15. And this is your amount, $200,000. The payment therefore will be for 12 times 15. I don't know how many periods that is, but that's the payment amount per month. All right, so then we can do number of periods. So what we're saying here is if the rate is 7%, then you have a monthly rate. If the payment is $150 per month and the total balance is $8,000, how long is it going to take to pay this back? Well, it says 64.07 periods. So that might be, in this case, monthly payments, right? So here you can also calculate the payment towards interest. So when you have a loan of $2,500 and this is the annual rate and you divide on 12, then for every year you can compute how much is it going to be in the first year. Well, it's going to be $17.17 going towards the interest only. Is this the same one? Yeah, let's do the same thing towards principal, see how much we pay towards the principal. Well, we pay in $234.92. And now we can actually do an amortization schedule. So when I run this code, you can see this is the output. So I'm calculating the first 16 months of this amortization schedule. And if you look at it, what I'm doing, I am passing in a 3.25% rate that is going to be divided on 12 months. Therefore, whatever the number of periods, meaning monthly, that's half of a 30-year mortgage, I guess. So that's about 15 years, something like that, 180 months. And if you have a principal amount of your loan of $350,000, this is what your payment down will look like with cumulative interest. For example, in the 16th period, you're paying $2,459 as a payment. I mean, this is the same for every month, obviously. But as you can see, you're paying $885 towards your interest and $1,574 towards your principal. So this will keep climbing, okay? And this will keep being reduced. And when you hit the halfway point, that's kind of where it reverses. In any event, you can see the cumulative payments and interests towards principal in this case. And then you can see the remaining balance here after each payment. So that's an amortization schedule you can actually compute using the table macro. All right, very good. Now we're getting into net present value calculation. By the way, if you're interested, let me see if I have Excel open. So if you look here, here is my amortization schedule. And when you have this rate and you divide it on 12, you're getting this. 15 years times 12 is 180 periods. This is the present value of the loan, the amount that you actually are going to borrow for your house or what have you. And the payment, therefore, is $2,459. So if you look at this, let me see if I can bring it up and show you side by side here. So if you look at these numbers here, you can compare it to this orange border down here. So for period 16 here, you can see 24, 59, 34, 885, 1574, and so on. You can see these are pretty much the same numbers. So it computes the same thing as it does in Excel, in other words. Okay, so that's the amortization schedule. Now, that's part of the macro that we loaded in. You can also compute cash outflows and cash inflows in the traditional sense, meaning we assume equal time intervals here, and we assume a discount rate of 8% like this. When you run that, you're getting 3,065.22. So that's a positive net present value for 8%. Now, what we can do now is we can compute the internal rate of return. I am curious. Let's try this because I want to see what if I do the opposite here. And let me add a cell. This will be interesting. Okay, so what I did was I ran this query. And as you can see, because this is positive 3,065.22, here's the same cash flows. The internal rate of return is positive too. It's 10.58%. So that's why this is positive. You can see here it's a positive internal rate of return. All right, so here's some more internal rate of returns. So let's run that so you can see another example. 28.9%. Number of iterations. In that code that I put forth in for the macros, it iterates through it and it tells you it's doing 16 steps. So it converges 16 times using the method that calculates the internal rate of return. So this Newton-Raphson method is not 32 steps, but it's 16 steps. And those are the ones listed down here, as you can see. You're getting to 16 steps down here. And then you see if it converges. Okay, so there's a method used to compute this. And you can see it used 16 steps, but it did converge. And this is the internal rate of return it came up with. All right, so that seems to be working. Now, you can also do annualized internal rate of return. And the way you can use a lot of data here because it's monthly data. So you can compute the monthly internal rate of return. Now this one is a formatted one and this is a formatted annually return. So let's run that and see what that looks like. As you can see, 0.7701% is the monthly return. But when you annualize it, it becomes 9.64%. And again, you can use this method here in order to annualize it. So you're making it to the power of 12, in other words, and you subtract 1 from it here. And again, to make it look nicer, we multiply by 100. All right, so this is the modified rate of return. Okay, so what is the difference between internal rate of return and modified internal rate of return? Well, the core difference is that it lies in the reinvestment assumption. The internal rate of return assumes that the interim cash flows are reinvested at the same rate as the rate of return itself, which is often unrealistic, obviously, and optimistic. The modified internal rate of return assumes that the positive cash flows are reinvested at the cost of capital. That's the reinvestment rate. So it provides a more realistic and conservative, most likely a lower and more accurate measure of profitability. So that's the difference between the two. So here we're going to compute the modified internal rate of return, and that is negative 3.1. That's not even a positive rate. There's also the XIRR and XNPV, and the difference between a regular IRR and the regular NPV is now that you have unequal cash flow based on dates. So if you look at my input here, you have a discount rate, you have the cash outflows and inflows. So this is the initial investment. These are the expected cash inflows. But they're not going to happen like, say, monthly or anything like that. They're going to be spaced out. So in this case, we're saying here is when we invest, the initial investment, this one. And here is our first cash inflow. It's going to happen on June 1st. The second one is going to happen in 2026 on January 1st. And the third one on this date and so forth. So these dates are not in equally spaced intervals. So that's what makes it a more realistic way of computing this if you know when it's going to happen, obviously. If it's just a guess, then you might as well use the regular NPV, right? So let's see what that looks like. Well, we'll run that, and it comes back with $86.20. Now, what rate do I have to solve for in order for making my XNPV equal to 0? And in other words, that means you're solving for the internal rate of return based on the same input, okay, these same input data. And the difference, of course, is the formula, right? This one. So if you look at it here, the rate will be 16.52%. Now what we can do, we can check for that. So if you look at the input up here, you can see that the XNPV, you have a discount rate like this, right? And then you have cash in outflows and inflows, and then the dates. In order to figure out when this NPV or the XNPV is 0, you have to find the rate at which it should be 0. And that's why we have this select statement right here, because we're solving for the XIRR where NPV is 0, or the XNPV is 0, based on the dates and the cash outflow and inflows. The answer should be 0, right? Now, there might be some numbers floating out here, but it's close enough to 0. So you can also compare this to Excel. If you open up Excel and you search for this XIRR, so like this, if I go to, for example, here, and I say equals XIRR, and now when I click into this function here, it will load an example of this. When you scroll down, you can see you have the formula here, this one, and you also have values. So you can basically copy this stuff like this and paste it in somewhere. Here, for example, make it a little wider. So it gives you this, 37.34%. So when I do the same thing here, using the same numbers and run this, here is this 37.34%. and it used 16 iterations and converged. So you can also do the same thing with the X NPV. And when I run that, it gives me 2086. And again, if you go back to Excel, you can look at the example yourself by changing this to, the rate should be first 0.09. So 2086.65, 2086.65. So we're getting the same result. Well, I hope this was useful. I hope you like my video. And if you do, please give me a like and consider subscribing to my channel. It'd be fantastic. I look forward to see you again in my next video. Take care, everybody. Bye-bye.